All right, good morning, sugars. We're starting with section 14.2. 14.2 today. All right, here we go. Chi-square test for homogeneity. That is a big word, but basically it just means, what does homogeneous mean?
The same.
The same. So what we're looking at is our null hypothesis is saying there's no difference. They are the same. And our alternative hypothesis is saying that there is a difference. Well, didn't we kind of do that yesterday with goodness of fit? Okay, so what we did yesterday was we took one bag of M&Ms and we had one categorical variable. And that one categorical variable was color of M&Ms. That was our category, right? Color. So we tried to look at the percentage that M&Ms claimed put in a bag, right? 10% of blue, 10% of red, and then we compared it to the percentages that we got in the bag. And we did an overall comparison. So we didn't just look at each, the red or the green or the blue. We looked at it as a total, but we did notice which ones contributed the most difference, okay? So we had that contributing factor down there in our test yesterday in the calculator. So, but today what we're going to do is we are going to take one categorical variable, which was the same thing we did yesterday, color of M&Ms, but we're going to do it over several populations. So an example would be if I was looking at color of M&Ms, and just go along with me, this is a bad example, or we were looking at color, but we had two different populations. We had M&Ms and we had Skittles, okay? Or we had M&Ms and we had Reese's, and we were looking at the color distribution. So that's my one categorical variable, but I had two separate populations that I was looking at, okay? Here's another one. What if I looked at GPA and I looked at University of West Georgia versus Georgia Southern? Two different populations, one variable. My variable would be GPA, okay? So that's what we're looking at. So that's going to be today, okay? And so what we're going to ask ourselves is, there's no difference in the distribution of GPAs between the two colleges, okay, the two populations, or there is a difference in the distribution of GPAs in the two different populations, the two different colleges. Yes, sir. Kind of, but it's still the chi-square distribution. It's what we did yesterday. But yesterday we just did one population. It was M&Ms. But today we're going to do two populations. We're going to do color like we did yesterday, and instead of M&Ms as my one population, what if we did color for M&Ms and Reese's? Now I have two separate populations, right? M&M's bag, Reese's bag. Same thing. So it's the same idea of what we did yesterday. It's still the chi-square. Still going to treat it the same way. Still going to do observed minus expected squared all over our expected. We're still going to do that type of thing, okay, and come up with a chi-squared. But just recognize that it's going to look a little bit different, okay? So yesterday what we did, we made a table, right? And we had colors here, and then we had some percentages down here, and it kind of looked like a table. And we were able to, do y'all remember yesterday? We were able to do list 1 and list 2 when it was a chi-square goodness of fit test. Y'all remember that? Well, today we're going to have we're going to have more information than that, so we can't use list anymore. So we're going to have to use something called a matrix. How many of y'all have done matrices? Is anybody in pre-calculus yet? Nobody's in pre-calculus? Okay. So a matrix is several rows and several columns. So a matrix is like a table, okay? So we know that we've seen tables that look like this before, where you have over here, you might have two variables that we're talking about, and then over here we might have two variables that we're talking about. Well, so that makes a table of information. I can't put a table into a list, okay? But what I can do is put it into something called a matrix. And so we're going to do that today, where I have several rows and several columns, okay? And your calculator does a lot of it for you, so you don't have to worry about that. But you are going to have to input the data, and then your calculator will take it from there, okay? So we'll do that. But you do need to recognize what type of test you're doing, and just so that your setup is appropriate. The rest of it, the calculator's going to spit it out for you, okay? All right, so this is the test for homogeneity. And if you look at this, we still have our conditions. We have our setup. There is no difference between the distribution of a categorical variable over several populations. There is no difference between the distribution of grades at several populations, at UGA, at Georgia Southern, at West Georgia. Okay, let me turn it on. Or my HA is saying there is a difference between the distribution of grades at the different schools. Okay, so I have different populations. All right, our conditions, these look a little bit different now because our expected counts yesterday was kind of easy to find. Today it's going to be a little bit different. We're going to have to use a different formula. Okay, random, make sure it's a random sample, random allocation, y'all know that. Okay, that's our SRS. And then our sample size, remember it's not normal because our chi-square distribution looks like this. So we still have our SRS, we still have some independence, but now we have to know our sample size, right? And expected counts are at least 5. Same rule as yesterday, expected counts have to be at least 5. So we can call this the number of expected counts. So we still have an N there, okay? So the number of expected counts. Izzy, just grab the papers off the front desk, okay? All right, so this is how we're going to find it today. We're going to have rows and we're going to have columns, just like I showed you guys, okay? So we're going to do row total times the column total divided by N, and that is our expected count. That seems like a lot of work, but guess what? Your calculator will do that for you too, okay? So once we input the data into rows and columns into our calculator, it will calculate the expected count. I will show you how to do it by hand, and then I'll show you how to do it in the calculator, okay? So we always have to know our expected count. Do you remember yesterday our chi-square formula looked like this? What was it? It was the sum of what? Observed minus expected squared all over expected. All right. So basically, we have to find observed minus expected squared over expected for every single item. For all the red M&Ms, the blue M&Ms, the green M&Ms, right? We had to do that. And then the sum means that we added them all up, right? Well, today we have more. We have our observed and expected, but it's going to be in a table form. So we just have a lot more to figure out. But again, the calculator will do it for you, okay? All right, so I'm going to show you how to do all that. And then obviously independence, all populations meet our 10% rule, that your entire population has to be greater than or equal to 10 times our sample size, okay? Degrees of freedom, by the way, is, remember our degrees of freedom, we always have to do 1 minus. Do y'all remember that? You have to minus 1. So we're going to minus 1 from our rows, minus 1 from our columns, and then multiply it together. So instead of row times column, it's row minus 1 times column minus 1. Okay, and that's our degrees of freedom. You need degrees of freedom, why? To do what? Yeah, to look at your table and find it on your table. But do I really have to use my table? No, I could probably use my graphing calculator instead, okay? So I'm going to show you how to do it all, but the best way to learn how to do it is to see an example. So we are going to pop down to an example on the back page. So I want you to flip it over right here, and let's talk about this, okay? All right, so Penn State has a main campus in the town of State College and more than 20 smaller Commonwealth campuses around the state. The Penn State Division of Student Affairs polls separate random samples of undergrads from the main campus and Commonwealth campuses about their use of online social networking. Okay? Facebook was the most popular site with more than 80% of students having an account. Here's the comparison of Facebook use by undergraduates at the main campus and at Commonwealth campuses, okay? I have one categorical variable, and then I have several populations. Let's label what is what. What are my populations, and what is my main variable that I'm looking at? So what is it? That's right. So Facebook use, this is my one categorical variable that I'm looking at. And then my two separate populations, this is one of my populations right here. And then this is my other population. All right, so we have a bunch of data. Y'all can see that it looks a little more expanded than yesterday. Remember yesterday we just had like color of M&Ms. Well, we could have changed it and done color of M&Ms and then like added weight or something like that. You know, you could always add an extra population there. All right, so now that we're looking at this, the question is, do these data provide convincing evidence of a difference in the distribution among Facebook use in the two different campuses? All right, so either there is no difference or there is a difference. That's my ho and my ha, right? So either there is consistency, it is the same among the Commonwealth campuses and the main campus, or it is not the same, okay? There is no difference or there is. So right here it says, is there convincing evidence of a difference in distribution? So that's what we should look at. So let's write our ho and our ha. Okay, our null hypothesis. What is our null going to be? What does null mean?
All the data is correct and normal.
Yeah, all the data is correct and normal. There is no difference at all. There is no change. There's no difference. We're going to use the word difference. They used it. So there is no difference. Null, none, zero, no difference in Facebook use among the two campuses, which are our two populations. Thank you, baby doll. Have a good day. Do you need a note or anything, or are you good?
No, I'm good.
All right, thanks, Mary Grace. All right, and then of course, what would our alternative be?
But is it different?
That's right. There is a difference. That is not a D. That's a candy cane. There is a candy cane difference, okay? In Facebook use among the two campuses. And just to let you know, y'all, you do not have to put these in numerical values. Words are okay. So words are good here. Forever I was like, there's got to be a number there. Why isn't there a number, right? So now what we're trying to do, but since we're looking at so much data, we're just going to say overall there is no difference or there is a difference, okay? All right, so right now I want you guys to decide, do y'all want to set an alpha level?
Yeah.
Okay, so you want to set an alpha level. It's of your choice. Before I start looking at the data, okay, set an alpha level before crunching numbers. You are allowed to set your own alpha level, but not after you've been like, oh, look at the data. It's right there at 4%, so I'm going to choose 5% instead of 1%, right? Because the 4% and then, oh my goodness. Okay, no, you have to choose it right then at the beginning. So what do y'all want to set it at? 0.05, sounds good. All right, so now we're good. Now we need to check our conditions and calculate our expected counts, okay? So was this an SRS? I believe they did say it. I read it. Yes, random sample at the top. Random sample. So yes. Okay, independence. Who did we sample?
Students.
Students. Penn State students, right? Okay. So I'm going to look at this right here. And capital N, this is all Penn State students, is greater than 10 times N. Well, do we know an N value?
What's your total?
Yep, our total. Where's it at?
Total effective users?
Yep. We do not have it quite yet though, do we? All right, so let me get a ruler and let's figure out our total. We're going to have to figure out our marginal distributions. That's dropping. Sorry, but I do need a little ruler or something? This will work.
Don't you just add 910 and 6?
You are, but I'm gonna do them all. We're gonna need them all because we're gonna do
Okay.
row totals and column totals. So I say, let's just go ahead and bust them all out right now. Oh man, I hope I packed my graphing calculator. Took it home last night. We already have our column totals. All right, good. All right, so we already have column totals right here. I need a bigger marker. Here are the column totals, and then we're going to do row totals over here. I'm going to grab my graphing calculator. Nobody wants to live without a graphing calculator. All right, so we have 1537. Let's go ahead and fill all these in. All right, 131. And 372. And 1034. Make sure that each row and each column, the row totals and column totals both equal 1537. All right, are we good now? Okay, so down here, all Penn State students, do you believe that that is 10 times 1537? Do you believe that's greater? So 1537. And do y'all think that there's going to be more than 15,000 students there? Between all campuses, all Penn State students? I would say so. How many students are at UGA? A lot. I know that there's like 12,000 at West Georgia. So it's got to be bigger than that, right? Okay. All right. So I'm good with that. I would say yes. Plus, logically, you could say that all of these students are independent of each other. Okay. Now, N is no longer normality because we're dealing with a skewed distribution. So this is the number of expected counts. So we need to make sure that all expected counts are greater than or equal to what?
5.
Greater than or equal to 5. So now I have to come up with my expected count. So I'm going to come up here, and in a different color, I'm going to come up with expected accounts or expected counts. What are all these numbers right here? What are these called? Observed. Okay, so now what I need to do is come up with all of my expected. Now the rule for that is right here, if you want to write it down, expected counts is row total times column total all over N. So we can calculate that. That's not going to be bad. So if I'm looking at this first one right here, 55, and this right here, the expected count, is on the front of your paper. That rule's on the other side. All right, so what is the row total for 55? 131. What is the column total? 910. And what is my grand total? 1537. So it's going to look like this. The row total, 131 times column total, 910, all over 1537. And that's what I would expect to get back. Yes, round to 2 decimals. And what did you get? 77.56. All right, so that's how you find your expected counts for each one of these, okay? And I'm going to go ahead and write down what I have found this morning. All right, so you have to do row times column for each one. I'll do it for this one again. Row times column divided by N. I gave you a little space on that first one so that you could try it and write it down. And now the rest of them you can just go ahead and fill in. All right, so that's what I got this morning when I did it. For those watching at home, I will take a picture of this and send it to you too, just in case you can't see my numbers. Okay, so now that I have that, I need to calculate the chi-square statistic. Oh, by the way, are all of my expected counts greater than 5?
Yes.
All right, so we're good to go. All right, so that is true as well. So expected counts greater than 5. Looks like we have passed all of our conditions. It's probably the first time in a month. Okay, so now that we have all those, now we need to calculate the chi-square statistic. Goodness. Now, remember, do you have to write all of the chi-square statistic? No, we can use our ellipses, the dot, 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 okay? So a chi-square statistic looks like this. Let me write down the formula. It is on your formula sheet. I believe y'all said page 1 of your formula sheet. And I know mine's way at the bottom of my sheet. Right there, observed minus expected squared all over expected. But you have to do it for every single one. So how many different observed and expected do I have here? 6, right? So there's really 6 of them, but I don't have to write all of them. So I'm going to start with 1. Remember, it is the sum of all of them. So my first one, let's go ahead and do the 55. So observed minus expected squared all over expected. Plus dot, 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 going down to my last one. Why don't we do the 394? Sound good? That seems like my last one there. Plus 394 minus 421.81 squared all over expected. 421.81. And you get a number back. The bigger the number, the further you are away from no change or no difference. What number is no difference? 0. So if you get a number close to 0, like 1, 2, 3, 4, 5, 6, 7, not too bad. You get a number like 33, you're really far, okay? So now, at this point, this is where our calculator is going to take over so that we are not in charge, okay? All right, so here we go. Now, you could do it all by yourself, and that is fine, but I gave you the idea. So now what we're going to do is we are going to go to Stat Calc, or Stat Test. I usually press down on my arrow. We are not doing a goodness of fit test. That is when you have exactly 1 variable, 1 population. Today we have 1 variable, 2 populations, okay? And we're going to go to C, chi-square test. And now I just want y'all to look at it so you understand what you're going to need. We press enter and it says your observed should be in matrix A and your expected will be in matrix B, okay? All right, so what we have to do is we have to go and do a matrix. So we're going to look down here, and do y'all see way down here below the math button, it says the word matrix. Do y'all see that? All right, so that's what we're going to go to. So I'm going to move this and, second matrix. All right, so here are our matrices, okay? So we have matrix A and matrix B. These are just the names of them. I have to edit them and get them to have the numbers that I want them to be in, okay? And we're not really doing math with them right now. So, all right, so I'm going to go over and edit, go to A. Now, I do not have a 3 by 3 matrix, okay? It is row and column. The same way that it is row times column, it's the number of rows and the number of columns. So, how many rows do I have with data? 3 rows, how many columns? So this is a 3 by 2 matrix. So I want a 3 by 2. And you just fiddle with it until it looks the way, if you accidentally put 2 by 3, it's not going to look like your table, so you know that you're wrong, okay? So 3 by 2. Now all you have to do is put in your observed, which is right here. 55, 76, 215. All you have to do is put all that in. So go ahead and put that in for me. And I think there's a shortcut, so if y'all will hang with me. book might not do. I know there's a shortcut, so I'm trying to find the shortcut for you. Here it is. Okay, so do you have your observed in? All right, now go to B. So now we're going to go back. Make sure you have them all in. Let me put them in real quick. Sorry, y'all. I think there's a way that your calculator will calculate your expected for you, and you don't have to do it. All right, so I'm going to try this. I don't think that you have to put your expected in. I think your calculator will do it for you. There's enough data there that I think it's already done it for you, okay? I'm not sure, but we're about to find out, okay? If we all get separate answers, then that means it's completely jacked up, and we're about to find out, okay? But I think that your calculator will do it for you. So if it doesn't work, then we'll know that in matrix B, we're gonna have to go back and put our own expected values in. Are y'all following me? I think it'll do it for you though. All right, so now I'm gonna go to stat, go to test. I do know that my observed are in A. I think it'll put your expected in B. We're about to find out. If it gives me an error, then I know I'm wrong. All right, I think that's right. Let me check. I have done this problem already. Hold on. All right, and I got 19.49. Is that what I got? Okay, so it already has them expected in there. So let's go back and check to make sure our expected values are in there. Go back to matrix, and now let's go to B and make sure that it really did plop in. So go to edit, and then go over to B. And are those the expected values that we found? Are those it? Yes? Are y'all impressed it did it for you? That's awesome. That's amazing. You didn't have to do it. This whole time I made you do all of them, right? Okay, guess what? It'll do it for you. So very good. I thought that it did, but I couldn't remember. All right. I've only taught this for 12 years, but for some reason I couldn't remember if it did it or not. All right, so it already has it in there for you, which is really awesome. You can rewrite and put those into, you can even write those down on the AP exam. Like it's already done it for you, okay? So now when I go back, let me get out of that, and go back and run the test. Let's talk about the meaning of that information. You can even draw it if you want to. See if it'll come up on my paper here. I probably have a million other things in there. Holy moly! Y'all, is that a skewed distribution? Can y'all even see the shaded area? Because look at my p-value. Is my p-value 1? No, it's 1 times 10 to the negative 4. So it's like 0.00001. Okay? That's insane. So our chi-squared right there is 19.489. So with that said, would you reject the null or fail to reject the null? Yeah, you would absolutely reject the null. How would you look up that 19.49 on your paper? Get out your blue sheet, and let's just say you did it all by hand, bless your heart, and you were wondering how to look at that 19.49. Let me write that down so that I have it on my paper. All right, so my chi-squared came up to be 19.49, and I got a p-value of approximately 0. All right, what is my degrees of freedom, y'all? If I had to look this up, I would have to know my degrees of freedom. Row minus 1 times column minus 1. How many rows did I have? 3. So it'd be 3 minus 1 times how many columns? 2 minus 1. So that is 2 times 1. So my degrees of freedom is 2. Got it? Now, how would I look up? I need to find I need to go to degrees of freedom of 2. And I need to look up the number closest to 19. So go to 2 degrees of freedom. And what is my number closest to 19? It's not picking that up very well. It doesn't like my blue paper. All right, the number closest to 19 is 15.2, way down here at the end, yes? So do y'all see how my p-values are getting smaller, 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 smaller? So that means if I'm beyond 13 and 15, I'm at 19, then that means my p-value will be less than 0.0005, right? Okay. All right, so that is a way that you could look it up if you were using the table. Okay, so down here we are going to reject HO with a p-value of approximately 0 and conclude there is a difference in Facebook use among our two populations, our two college populations. Boom! That's not that bad, is it? I know it took a second because I had to show you some stuff and all that good stuff. So the next one's exactly the same. Association and independence, it is absolutely the same. So you're going to use the same chi-square in your calculator, but it just looks a little bit different. So just understand, instead of saying difference, we're going to say the word association. Association, are they associated? Are they independent or dependent of each other? Okay, so that's going to be our last one that we're going to do. All right, so can I get rid of that? We're good? All right, next sheet. This is our last sheet. All right, the only thing difference, if you look at this gray box right here, 2 categorical variables tested over 1 population. I just did the reverse of that. I did 1 category on 2 populations, and now I'm going to do 2 categories on 1 population. So if I wanted to do the color of the M&M and the weight of the M&M, right? That's 1 population, 2 categories, okay? So this is 2 categorical variables in 1 population. So either there's no association or there is an association. Another way I like to put that is they are independent of each other or they are not independent of each other, okay? If there's an association, then that means they're not independent, right? There's no association, they're independent of each other. So that's kind of a way that I like to add on and write that in there. So they are independent or they are not independent. No association is an association. All right, so we only have 1 population here. I could do the population of all boys, and then I could do their height and their shoe size, okay? And or categorical variables. Let's see, I could do their, what's a category? Their hair color and their eye color. Thank you very much. All right, so that's what I could do here. All right, so here we go. What we're going to do here is your anger level. How happy are you or angry are you? And your heart disease. So we are going to ask this question. Do angry people have more heart disease? A study of a random sample of 8,474 people with normal blood pressure for about 4 years. They looked at all of them. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale Test. What's the acronym for that? STAST. What is that called when it's the same with forward and back? Is that the same for? No, it's not. It's not even. Okay. Do you know what I'm talking about? What is it called when it's the same? Palindrome. Thank you. All right. Today I was, see, look at that. Y'all are good for words. Okay. Each person took the test, which measures how prone a person is to sudden anger. Researchers also recorded whether each person developed coronary heart disease. This includes people who had heart attacks and those who needed medical treatment. Here's a 2-way table. So we have the same population of people, but we're testing 2 different items. All right, flip it. All right, so what type is this? This is association. We have 1 population of people. 1 population of people. That set of people that we had, 8,474 people. And we're trying to say, is there an association between how angry you are, angry people, and angry people, I guess, level of anger, and coronary heart disease. So we have actually two different categories. So here's one category. Category 1 and category 2 is coronary heart disease. Two categories, one population. What did I just do? I did one category, Facebook, and two populations. So it's just kind of the reverse of that. Still going to do the same thing. Still have a table, still doing a matrix, still doing expected counts, still doing chi-squared, still making a decision. Okay? Same thing. All right. Do the data. Don't you hate when it says do the data instead of does the data? All right. Data is plural and singular. Okay. Do the data provide convincing evidence there's an association between anger level and heart disease? Okay? So let's do a ho and a ha here. Okay? All right, what is my HO going to be? Okay, no association. Let's see, there is no association. Null means no association. Just steal their words between anger level and CHD, coronary heart disease. Okay, that means that they are independent of each other. I could throw some probability and independence in here for sure. Do y'all remember this? I'm just going to throw this out there because I want y'all to say things that make you go home. All right, so could I do the probability of coronary heart disease is equal to, this is our independence rule. I totally want you guys to start thinking back to chapter 6. All right, probability of coronary heart disease is equal to probability of coronary heart disease given anger level. Right? So if I pick like super duper, I'm crazy angry, the probability of coronary heart disease should be the same as the probability of coronary heart disease, right? No matter what the anger level is. And that would show independence, right? You could really do that for all of these rows and columns, for each one of these entries. All right, so just think about that. Now down here, there is an association. What is easier than that? Doing a chi-square. Dot, 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 dot. All right, do y'all want an alpha level? Pick one. 5%? Is that what y'all said? Okay, was it random? Yes, they did say random, didn't they? Okay. So this is our SRS. Here's our independence. N is number of samples must be what? Number of expected counts must be what? Greater than or equal to 5. All right, so this is our, now what is our population of interest here? Population of interest. People. It's really just people with normal blood pressure. That's right. That may or may not have anger issues. All right. So people. So I believe that this is people with normal blood pressure. So do you think that we are going to pass this rule right here? Yes, I hope so. All right. There you go. Yes. All right, large sample size. Our expected counts have to be greater than or equal to 5. Can I find that using the calculator? Yeah, we're going to do expected counts on that. I am going to write down all my expected counts, but it's because I'm about to cheat and use my calculator and let my calculator do it once I run the test, okay? So I have all my totals. Remember expected counts, just in case you need to remember the rule here. Expected counts is row total times column total divided by what? N. Good. All right, but again, our calculator will do that for us. So we're going to do that. All right, so let's hop to the calc. All of that you could do by hand, and that's not a big deal. All right, so let's go to matrix. Again, is down here right below math. And let's count our number of rows and our number of columns. How many rows do I have? 2. How many columns? So this is a 2 by 3. So go to edit, and we're just going to edit the first one, 2 by 3. Make sure it looks the way that you need it to, and start putting in your information. Notice you don't put totals in, you just put the entries in. These little things are called entries. All right, once I have my matrix A set, what do I do? Go to a what? Go to a test. Stat, test. Arrow up, and you can get straight to that chi-square. All right, my observed is in A, matrix A. It will automatically put my expected in matrix B. All we have to do is go and calculate. Whoa, whoa, look at my p-value. Times 10 to the negative 4. It's kind of small. So my p-value is not 3.22, is it? No, okay. So my degrees of freedom is 2. How do we know that? Row minus 1 times column minus 1. Okay, same as last time. And we have a chi-square of 16.07. So let's write that down. Again, it's good to show one step of this. Now that I know what my expected counts are, I'm just going to come back up here, and I'm going to put my expected counts in. How do I find them? They're in matrix B. Go to edit, go to B, and here are my expected counts. I need to have some to work with. Now, all of these are called contributing factors once you subtract all of these and do your observed minus expected square over expected. The ones that are the biggest are the ones that contribute the most. Tomorrow's warm-up, by the way, is you have to guess which chi-square to use, okay? All right, so now that I have all of those in, I can show just one time down here, I can show my chi-square being used. So I'm going to just start with my first one, the 53 minus 69.731. Plus, dot, 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 plus, and then do your last one. And that gives us our chi-square, which I didn't write down, of 16.076, or 77 if I rounded. Can I do that? Yep. All right, so my p-value came out to be approximately 0, or you can move it your decimal place. Move it 4 times. 1, 2, 3, 4. All right, teeny tiny. So what are we going to do at this point? Our P is less than alpha, correct? Okay, so we are going to reject HO and conclude. Now go steal and put your p-value in there. It's approximately 0. Steal this right here. And conclude that there is convincing evidence that there is an association between anger level and heart disease. So just steal the words and conclude there is. All right, that's not too bad, is it? Calc does a lot of the work for you, so that's a good thing. I'll take pictures of these and I will put them on Google Classroom. Remember, if you do end up getting quarantined for some reason, I'm putting everything up there, okay? I hope to have your review by tomorrow to you. I have your test, but I've got to make up a review that matches it for you guys, okay? All right, and your homework tonight, I'll be handing out to you right now, okay? All right. Bye, sugars.